Hey everyone. For my research presentation in natural language processing, I chose to look into the topic of XLNet. So today, I'm going to give you a presentation on why you should care about XLNet. So the title of the paper that we're going to discuss is XLNet, Generalized Autoregressive Pre-training for Language Understanding. I've listed the authors below, and they are from Carnegie Mellon University as well as the Google AI Brain Team. This paper was published in 2019, so while AI has changed a lot since then, I still think it's important to look back into how XLNet made the landscape change. Throughout the presentation, I'm going to ask you to keep two questions in mind, and at the end of the presentation, we'll answer them. But while we're talking about the paper and its results, you can think about the answers to these questions. First, how does the process of training XLNet differ from the process of training BERT, and why does XLNet implement this change? The other question is, what advantages does the Transformer XL backbone give XLNet as opposed to the standard Transformer architecture? We'll begin this discussion with a brief overview of traditional language modeling. And as we've seen in class, this ends up being a game of predicting language. And sometimes that's as simple as just guessing the next word in a sentence given the prior words in that sentence. Traditional approaches to this problem involve recurrent neural networks or long short-term memory networks, which operate via predicting words sequentially from left to right. But we've seen that these methods have some limitations, especially when it comes to modeling complex sentence structure. The first issue is that these models struggle to capture long-range relationships between words. So the farther apart two words are, the tougher it becomes for these models to connect them. The other issue is that sequential processing just ends up being less efficient than parallel processing, which many modern methods rely on. But BERT poses a solution to the problem of establishing long-range relationships between words. It stands for bidirectional encoder representations from transformers, and it is unique because it reads text both left to right and right to left simultaneously, so it reads it bidirectionally. And this gives the model a more comprehensive understanding of overall context, therefore giving it a more comprehensive understanding of overall meaning. And that's really important in natural language processing. But BERT is not perfect. In fact, it introduces some new issues. BERT is a masked language modeling process, which means that it hides some words during training. The problem with this is that the masking disrupts the natural flow of language during training, which may teach BERT to disrupt its own natural flow of language in processing. This means that when BERT is fine-tuned on real-world tasks, it may not handle word dependencies as well as we'd like to. And this is why XLNet was designed, to specifically overcome these issues. XLNet learns from the entire sequence without hiding words, and this is why the paper showcases XLNet and its abilities by comparing it to BERT directly across a variety of metrics. Overall, XLNet aims to develop a stronger understanding of context, and it is driven by two concepts at its core. The first is its permutation-based language modeling approach. Words are shuffled or permutated during training, and the model learns all possible ways that words relate to each other because of this shuffling. And because the model is permutating all these sequences of words all over the place while it trains, it gives itself a more complete picture of context. And these permutations enhance the autoregressive modeling process because traditional models only predict the next word based on previous words, but XLNet predicts words in all possible orders due to permutations. And this is the big picture of XLNet. It equips itself to learn both past and future contexts, like BERT, without disrupting the flow of language. So while you get the advantages of BERT in this bidirectional interpretation, you do not disrupt the flow of language, which is a risk that comes with BERT. So you get the best of both worlds. The architecture of XLNet is driven by the Transformer XL backbone, which operates based on two principles that are not present in the normal transformer architecture. The first of those components is segment-level recurrence, which overcomes the fixed length limitation that we know is attached to standard transformers. Transformer XLs overcome this issue by using hidden states to summarize old context when predicting new segments of text. Transformer XLs also employ relative positional encoding instead of absolute positional encoding, which helps models focus more on distance between words rather than absolute positions of words. And this becomes useful when dealing with long sequences of words where position becomes less meaningful. XLNet also utilizes a two-stream self-attention mechanism, which involves a content stream processing the actual words and their meanings, as well as a query stream, which determines which context is the most important for predicting the target word. This is the paper's figure for their two-stream self-attention mechanism. On the top left, you can see the content stream, which works like standard self-attention. Each word can attend to itself and other words in the sequence. On the bottom left, they depict the query stream, which prevents a word from attending to itself and ensures that when predicting a word, XLNet does not cheat by seeing the real answer. On the right half of the image, you see the permutation-based training phase. Instead of training in left to right, XLNet shuffles the words and forces the model to learn from all possible word orders. And as we said before, this preserves the bidirectional context without needing to mask the words like BERT does. So when it came to small-scale performance, XLNet outperformed BERT across a variety of metrics. We have things like the SQUAD here, which is the Stanford question answering dataset, and that measures how well models answer reading comprehension questions. We also have RACE, which is the reading comprehension dataset for exam questions, and that is designed to test how well models can handle complex reasoning questions. So on both of these, Excel significantly outperforms BERT by a sizable margin here. And as we scale up the problems, and these models are forced to undergo a lot more computations, XLNet outperforms BERT as well as Roberta and GPT and BERT plus DCMN. So XLNet is still a very strong performer even when you scale up these problems. And you can see that the result holds for the SQUAD as well. As you scale up the problems, XLNet is still the best performer here. XLNet also yields lower error rates than BERT and our other models when it comes to scanning a variety of these data sets, right? IMDb, Yelp, Amazon. Throughout all of them, you see that XLNet yields the lowest error rate. And finally, XLNet generally scores higher than BERT on the GLUE benchmark, which is the General Language Understanding Evaluation benchmark. And this includes a variety of tests. As you can see here, all of these tests are a part of the GLUE benchmark. And XLNet scores higher than BERT across many of these tasks, right? Including sentiment analysis, sentence classification, and question answering. Not all of them, right? You can see RTE, XLNet does not. Well, XLNet does score higher than BERT on RTE, but not Roberta. It's not the best performer of all the judged models here. XLNet marks an important step forward in language modeling. The big picture is that it enables bidirectional context processing without masking, which addresses the cons of BERT while still delivering all its pros. It also performs with higher accuracy and lower error rates than BERT on well-established benchmarks. And this marks important progress towards solving the general problem of context understanding in language processing. Some important future directions that could further the scope of XLNet are that we could further optimize the efficiency of the permutation-based training algorithm, and we could extend this technique to other multimodal data formats. But now, let's revisit those questions I asked you at the beginning of the slideshow. The first one was, how does the process of training XLNet differ from the process of training BERT, and why did they make this change? Unlike BERT, XLNet implements a permutation-based language modeling approach, shuffling words during training. As a result, XLNet gains a clearer picture of context by learning all possible ways that words relate to each other. Now for the other question, what advantages does the Transformer XL backbone give XLNet as opposed to the standard Transformer architecture? The Transformer XL backbone relies on segment-level recurrence and relative positional encoding to overcome fixed-length limitations and deal with larger datasets. But here is the full citation for the paper, and thank you all so much for listening to my presentation.